Hey, and welcome back to DATQVAULT video lectures. In this video, we're going to talk about oxidation and reduction. In specific, we're going to talk about oxidation of alcohols to carbonyl compounds, and we're going to talk about the reduction of those carbonyl compounds back to the corresponding alcohols. So first, we're going to look at oxidation of alcohols. We can oxidize alcohols, secondary alcohols to ketones. We can oxidize primary alcohols to the corresponding aldehydes, and we can also oxidize primary alcohols to the corresponding carboxylic acid. So, what are we talking about when we say the word oxidation of an alcohol? In specific, we're talking about the oxidation of this central carbon right here. And when we're talking about oxidation, we're talking about changing the formal charge on this central carbon. And we're doing that by either creating more bonds to that central carbon, to oxygen, or even in the case of oxidizing to a carboxylic acid, we're creating bonds to even more oxygen atoms. So we can do this by using a number of reagents, but this lecture is specifically going to focus on which reagents in particular will accomplish these specific chemical transformations. Also, we can look at this in the complete reverse direction, which is known as reduction. So we can reduce these corresponding carbonyl compounds back to the alcohol. We can reduce ketones back to secondary alcohols. We can reduce aldehydes back to primary alcohols, and we can even reduce carboxylic acids back to their corresponding primary alcohols. When we talk about reduction, we're focusing on the reduction of these central carbons. It's pretty much the opposite of oxidation in the fact that we are changing the formal charge on the central carbon to have less bonds to oxygen. So we're reducing carbonyl carbon-oxygen double bond to a carbon-oxygen single bond, or we're in the case of carbonyls completely removing an oxygen atom from that central carbon. If you don't remember exactly what formal charges are and what they stand for, there's a lecture that really hits on formal charges and what it means. So I suggest going back, checking out that lecture. All right, so again, we're looking at which reagents in general will accomplish these reduction reactions back to the alcohol from the carbonyls. All right, first let's focus on oxidation. We can do this using aqueous chromium-6 reagents. Typical aqueous chromium-6 reagents include chromium tetroxide or potassium or sodium dichromates. When these reagents are used to do an oxidation, these oxidations are called Jones oxidations. All right, so what do these specific Jones reagents do, and when we're talking about oxidizing alcohols? Here's a couple examples. Our first example is a primary alcohol, and our second example is a secondary alcohol. Here we're using a couple of different Jones reagents. Like I said, all three of these will work in the same manner, but for them to work, you must do them in the presence of strong acid. In this case, we're using sulfuric acid. So if we mix a primary alcohol with potassium dichromate and sulfuric acid, we are going to oxidize this alcohol all the way up to the carboxylic acid. Very important. If we do the same reaction Like I said, all these three reagents are interchangeable, but if we do the reaction in the presence of a secondary alcohol, we will oxidize it up to the ketone. Notice we cannot oxidize a ketone any further because there are no other hydrogens to replace with a carbon-oxygen bond. Alright, so what does the mechanism look like for an aqueous chromium 6 oxidation? First we have our reagent over here, which is in this case sodium dichromate. Like I said, it has to be done in the presence of a strong alcohol, such as sulfuric acid. So here we have sulfuric acid. First thing that's going to happen are these oxygens are just going to become protonyl by the strong acid, and we end up now with chromic acid. What this chromic acid does is it will then react with our alcohol. It'll do that by exchanging the alcohol for one of these OHs on the chromic acid. Once this happens, we form what is called our chromate ester. This chromate ester will then be deprotonated by a hydroxide that we lose from the previous step. And then this deprotonalization will end up giving us our oxidized alcohol. In this case, we're going to get a ketone from this specific substrate up here. Alright, so oxidation can also be done using non-aqueous chromium 6 reagents. Very typical non-aqueous chromium 6 reagents include pyridinium dichromate, which is this guy right here. This is commonly abbreviated as PDC. We can also use pyridinium chlorochromate, which is abbreviated PCC, and is this reagent right here. Using non-aqueous chromium 6 reagents, we do not have to use concentrated sulfuric acid for the reaction to go, and because of that, these are far milder oxidation reagents. And I'll show you how that is. So here we have an example of PDC acting as an oxidant on this primary alcohol. If we were to use a Jones reagent, for instance, this primary alcohol would be oxidized all the way up to the carboxylic acid. But since PDC and PCC are far more mild oxidizing reagents, they're only going to oxidize this primary alcohol up to the corresponding aldehyde. Here's another example of PCC in use on a secondary alcohol, and PCC or PDC will also oxidize secondary alcohols up to the corresponding ketone. Like I said earlier, PDC and PCC can be used interchangeably, and they will react identically in the case of primary and secondary alcohol oxidations. Alright, so let's go ahead and do a practice DAT question. Here we're asked what the product is of the following chemical reaction. So we're using PCC in an oxidation. And take a second, pause the video, figure out what our product will be from this oxidation. And then we'll solve it together. Alright, now that you've had a second to try to solve this oxidation question, we'll go over it together. On the real DAT, it's going to be computerized, so you're not going to get to draw on the exam itself. Instead, you're going to be given like a dry erase board with a whiteboard marker, which is represented over here by this empty box. So, first thing that I would do is to tackle this problem going through like a process of elimination almost. So we just have to recall what we know about the PCC oxidation reagent. We should know that it's a mild oxidation reagent. So in the case of aldehydes, in the case of primary alcohols, it will not oxidize them all the way up to a carboxylic acid. It'll only oxidize them to the corresponding aldehyde. So that actually eliminates a lot of our choices right away. Here we have our primary alcohol, and options B and E we can eliminate right away because it's showing them being oxidized all the way to the corresponding carboxylic acid. We know this reaction actually goes because PCC is an oxidizing reagent, and it will oxidize both primary and secondary alcohols, so we can also eliminate A, which states that no reaction will actually occur. So that just leaves us with C and D. The only difference between C and D is that the secondary alcohol is being oxidized in one case and it's not being oxidized in the other case. We know that PCC will, in fact, oxidize secondary alcohols to the corresponding ketones, so that eliminates D as a possible answer, leaving us with C as the answer to this question. So I know it's kind of getting a little bit complicated so far in the fact that we're going to have to memorize all these different oxidizing reagents for alcohols, but just need to realize I do realize that some of you might be wondering, when will I ever need to know this if I'm going to be a dentist? But really believing that kind of thinking, I think is definitely cancerous to your education. So the basic sciences are really foundational to further courses in science. Although you might not be doing any chemical reactions as a dentist in particular, having a basic understanding of the building blocks of science will really allow you to have a more in-depth understanding of other courses such as physiology, anatomy, or even pharmacology. And reduction and oxidation reactions are really a perfect example of that, as it applies to so much more than just organic chemistry. Even though you might be using reduction and oxidation in a very different light in organic chemistry, it really applies to so many more subjects, and being able to see these reactions happen will really help you understand reduction oxidation in other courses. So now let's talk about reduction of carbonyl compounds. There are really going to be two typical reducing agents that you're going to see on the DAT. And they include sodium borohydride, and the second one being lithium aluminum hydride. The major difference that you're going to need to know between these two reducing agents are that lithium aluminum hydride is a much stronger reducing agent than sodium borohydride. Second thing you're going to need to know about these reducing agents is that they both act as a hydride donor. So it's basically a source of H-, which is very nucleophilic and will reduce carbonyl compounds in that manner. Give you some examples here. So the first examples we're going to look at are aldehydes. So sodium borohydride, like I said, is the milder reducing agent, but it is still strong enough to reduce an aldehyde to the corresponding primary alcohol. And this works kind of the same way for all carbonyl compounds, is that this hydride source, this source of H-, will come in and attack the carbonyl carbon and kick the electrons up onto oxygen. And then this lone pair of electrons on oxygen will then grab a proton from some sort of a protic solvent, in this case methanol, which is a good solvent for sodium borohydride reductions, and then you get your corresponding alcohol. Lithium aluminum hydride also works as a fantastic reducing agent for aldehydes, and it works in the same manner. It's just a stronger reducing agent. So lithium aluminum hydride will probably be an overkill for reducing aldehydes of the corresponding alcohol, but it works in the same manner. You use water as a second step in the reaction of a lithium aluminum hydride reduction, in the same way that the corresponding oxide will be protonalized by water, just like how it was here with methanol. Lithium aluminum hydride is commonly used with ether and THF as solvents. This is why we use water as a second step for the protonalization step to get our corresponding alcohol. So just to review this concept, aldehydes can be reduced by both sodium borohydride and lithium aluminum hydride to the corresponding primary alcohols. All right, let's talk about ketones. So sodium borohydride again is a strong enough reducing agent to reduce ketones to the corresponding secondary alcohols. Also, of course, if sodium borohydride works, lithium aluminum hydride is definitely going to work to do the same reaction to reduce ketones to the corresponding secondary alcohols. All right, so let's look at the reduction of the carbonyl compounds known as carboxylic acids. So here is where you're going to see a major difference between lithium aluminum hydride and sodium borohydride. Lithium aluminum hydride is, of course, the stronger of the two reducing agents, and because of that, it's going to be able to reduce a carboxylic acid all the way down to the corresponding primary alcohol. But if you look at sodium borohydride being the weaker reducing agent, this is where the difference actually takes place between the two reducing agents. Sodium borohydride is not a strong enough reducing agent to reduce the carboxylic acid all the way down to the alcohol. So if you mix these two things together, you are going to get absolutely no reaction to happen. Alright, so you can reduce aldehydes, ketones, and carboxylic acids. You can also use these two reducing agents to reduce esters. Lithium aluminum hydride will reduce an ester down to its corresponding alcohol, and it does this by first, of course, cleaving the carbon-oxygen single bond, which will give you an aldehyde, which will then be reduced again to the corresponding alcohol. From this reaction, your byproduct is also going to be methanol, since you're cleaving that ester bond. Sodium borohydride is, again, just like in the case with carboxylic acids, not a strong enough reducing agent to actually fully reduce an ester down to the corresponding alcohol. So if you mix these together, you're not going to get any reaction whatsoever. Alright, let's go through and do a pretty tricky practice problem, a DAT style problem. Here we're asked what the reagents are for this transformation from this diol all the way up to the carboxylic acid. So first, you're going to be doing some sort of a oxidation followed by a reduction. So why don't you take a second, pause the video, and try to figure out what the answer is for the reagents necessary for this reduction, followed by oxidation followed by reduction. Alright, now that we've had a second to figure this out, we're going to solve this together. So the first thing that we need to do here is an oxidation, because we can't reduce these alcohols anymore. They're fully reduced. So we need to find the proper reagents to oxidize both this alcohol up to the corresponding ketone, and then also be able to oxidize this alcohol all the way up to the carboxylic acid. So we need a strong enough oxidation reagent to oxidize the primary alcohol to the carboxylic acid. That is really our key point. So which oxidation reagents are strong enough to do that? Well, it's going to be the aqueous chromium reagents. So we need a either chromium trioxide, or potassium or sodium dichromate in the presence of a strong acid to be able to do that. So we can start actually eliminating some choices that way. We can eliminate A because PDC is not a strong enough oxidation agent to oxidize all the way up to the carboxylic acid. Also, we can eliminate C because PCC will do the same thing. So now we're left with either B, D, or E. So the next step after we get oxidation is to be able to selectively reduce the compound that we get from the oxidation down to this compound right here. So in order to do that, sorry, this should be a carboxylic acid, we need to pick the correct reagent to be able to do this reduction. So we need a reducing agent that is strong enough to be able to reduce this ketone, but not strong enough to be able to reduce this carboxylic acid back down to the alcohol. So in order to do that, we have basically two options here. B, we have lithium aluminum hydride to do that. And option D, we're also using lithium aluminum hydride. But in option E, we're using sodium borohydride. Sodium borohydride, if you remember, will not reduce a carboxylic acid down to the alcohol. So that's a safe choice to be able to use to do the reduction of the ketone in the presence of the carboxylic acid. So we'll choose E as our final answer. Alright, so covered reduction and oxidation of carbonyl and alcohol compounds. So just want you guys to remember to work really hard on this stuff because getting a point or two higher on the DAT really may be the difference between gaining admission or not to a dental school. And it can also mean the difference between being able to select the school of your choice, which might be very, very important to you. So study hard on this stuff and definitely go ahead and take some practice exams or do some practice problems on the reduction and oxidation of alcohol and carbonyl compounds.